Alright, in this video we'll look at properties of liquids. Some select properties are viscosity, capillary action, and surface tension. First, viscosity. It is known as the resistance to flow. The more viscosity something has, the more slowly it flows. In your textbook you can see these two different types of oils. One flows faster than the other one. This one is said to have a higher viscosity. You can see it in a chart in 11.5 right here that the more atoms, and therefore the more electrons, and therefore the more intermolecular forces something has, the higher the viscosity and the larger the number. So the more intermolecular forces something has, the more viscosity that something possesses. Here's a little image of viscosity going from water to milk to oil to light syrup, heavy syrup, and then chocolate syrup. And the stickiness for each one of these caused by stronger or more numerous molecule-to-molecule interactions causes the molecules to stick better together. In cooking terms, which all these are in, the more viscous solution can appear clumpier and has a less viscous solution appears to be more runny. So waters are more runny right here, and then we can see chocolate syrup right here. You know, that's super sticky and sticks together because it has stronger intermolecular forces right here. So stronger intermolecular forces here, weaker intermolecular forces down here. That's what causes viscosity. Our second force is called surface tension. The surface tension occurs only on the surface of a liquid. And I have a diagram right here for you that I tried to draw on paper. You can give it a try as well. But these are the little surface molecules of water. And I tried to draw the surface right here, the liquid surface molecules. And then I picked one molecule like they did right here and showed how it's only attracted down and to the sides of the liquid. Whereas a molecule in the interior portion of the liquid would be attracted in all directions, left, right, top, bottom, side, side. Since the surface of the liquid is special and is only attracted in three different ways, not up as well, only down and to the side, it allows a skin to form on the top of the surface, and things like bugs and lightweight pieces can appear to float on top of water, for example. More strongly bonded molecules form this surface tension on the top and then allow things to appear to float. Water is the perfect example of that. Versus the interior portion where it pulls in all directions. So let's take a look at an image of this. So here's an image of the surface tension of a green bug on top of some water, and then you can see the water molecules right here are pulled in all directions except up, but the water molecules in the middle here are pulled in every single direction, so they're more strongly attracted in the middle than on the top. They're only attracted in certain directions. So you can see you can float like a paper clip on top of water because water has that surface tension. Here's another nice diagram. In this one you can see that the force is directed to the interior of the substance, whereas inside of the substance is only it's directed in all different directions. And you can see right here that a small substance would float or appear to float on top because the surface tension would actually like pull these pieces inside and then buoy that substance back up. So here's another example of the molecules being pulled in all different directions inside, but on the surface it's only side to side and down back in. This is what it calls water to bead up too, because on the surface of the water, which is all around the edges, it's pulling in towards itself. And this surface tension causes the water droplets to form like a curvy surface on them right here. Whereas inside, of course, they're pulled in all different directions. Another example a needle floating on top of water like this. Atoms on the surface are attracted to one side and down, whereas inside they're attracted every single direction. This gives us really unique properties for water, because water, of course, pretty popular for us, and it allows things to float on top of it that really shouldn't. So surface tension is the second type of special property of liquid that we're going to look at. The third kind is called capillary action. Capillary action happens between polar molecules and substances that have positives and negatives, for example, glass. And so when you put water inside of glass, water is made of H2O molecules, of course, that have a dipole moment and a positive and negative interaction, which are these little red dashed lines right here. And then the silicon dioxide that makes up glass, that also has positive and negative parts, because silicon and oxygen have different electronegativities, and so this hydrogen is actually slightly attracted to the glass. This allows the water to appear to pull up against the glass. Not only appear, it actually does pull up against the glass, and it forms this concave surface that we call a meniscus. Whereas if you look at a different liquid, like mercury, for example, this mercury right here, notice how it forms like a bubble on top of itself. That's because mercury is nonpolar. It's just Hg with some electrons, and it only sticks to itself. It doesn't stick to polarized things like this silicon dioxide right here. And so you can see that it actually forms a convex surface right here on the top. So the cohesive forces inside of mercury right here actually stick the mercury together, whereas the cohesive forces of water right here are overcome by the adhesive forces of the glass and allow the water to like pile up on top of itself and cause that meniscus. So here's a couple of pictures of capillary action. So let's focus first on this one. Capillary action is the difference is that water is polar and it adheres to the glass walls of the tube. So you can see this surface right here. Whereas mercury, on the other hand, has this convex surface right here because mercury only attracts to itself and inside. So here's a couple of examples of capillary action. You can see that the smaller the tube, the more water is attracted to the glass and the more it's pulled up into these little tubes. And this is another example right here where you can see water is pulled up on the sides of the tubes right here, and the skinnier the tube, the more it seems to be pulled up because of this capillary action, or the water's attraction to the glass. Whereas mercury right here, that doesn't have any want for attracting to the silicon dioxide right here. Here's another example of the surface tension that causes the capillary action right here of the water. Pulling up of that water inside of here, inside of the tubes. You can see this capillary action happen inside of these little towels right here too, and you can see that the water sticks to itself and is actually like pulled along because of the attractive forces, not only between the water, but between the water and the medium that's holding it, whether it be a paper towel, whether it be something that's glass and is therefore pulling up inside of the little glass tubes, or it just happens to be the mercury, of course, is the opposite example, that the substance that's pushing back or not adhering to the container that's holding it. So those are our three special properties. Special properties, once again, were viscosity, surface tension, and capillary action.